Molecular geometry, molecular polarity, polar molecules. In this tutorial, we will be looking at polar molecules composed of polar covalent bonds, examples, and more examples. Polar molecules composed of polar covalent bonds. Polar molecules contain polar covalent bonds. However, the geometry of the molecule is an important factor when determining overall molecular polarity. Polar molecules possess a molecular geometry that results in an asymmetric distribution of charge and produces a net molecular dipole. If all the individual bond polarities, in other words, the bond polarity arrows, do not cancel, the molecule is polar. If a non-bonding or lone electron pair is present on the central atom, the molecule will most likely be polar, but there are some exceptions. Exceptions include molecules with linear and square planar molecular geometries. Let's look at our first example, hydrogen cyanide, which has a linear molecular geometry. When determining whether a molecule is polar or nonpolar, the first task is to examine the molecular geometry along with the types of elements involved. The next step is to determine whether or not the bonds are polar. This can be done by assigning electronegativity values and seeing if a dipole moment exists. So hydrogen is 2.2, carbon is 2.6, and nitrogen is 3.0. By taking the differences in the electronegativity values, we can see that all of these bonds will be polar. Next, polarity arrows are used, pointing from the less electronegative element to the more electronegative element. So in this case, we will have a polarity arrow between the hydrogen and the carbon, pointing from the hydrogen to the carbon, and then another polarity arrow pointing from the carbon to the nitrogen. A net dipole moment is determined from these polarity arrows, and the molecule is found to be polar. So we will use a blue arrow showing a net dipole, since the hydrogen is the least electronegative and the nitrogen is the most electronegative. Lowercase delta symbols are used to show the slightly positive and slightly negative ends of the molecule in the polar molecule. So in this case, the hydrogen, represented by this white sphere, will have a slightly positive sign associated with it, and the nitrogen, represented by the blue sphere, will have a slightly negative sign associated with it. Our next example is sulfur dioxide, SO2, and this is an example of a bent molecular geometry. So the first thing that we're going to do is look at our molecule, and we can see that it is composed of 2 oxygen atoms and 1 sulfur atom. Next thing that we're going to do is assign electronegativity values. So sulfur has an electronegativity of 2.6, and the oxygen has an electronegativity of 3.4 and 3.4. Then we're going to use polarity arrows pointing from the less electronegative to the more electronegative element, as we can see right here. Then, after looking at both of these polarity arrows and seeing that these bonds are both polar covalent and therefore having a dipole moment, we can find the overall net dipole moment and represent it as this blue polarity arrow pointing downwards. So a non-bonding lone electron pair right here is present on the central sulfur atom, compressing the sulfur-oxygen bonds into a bent molecular geometry. In other words, the bond polarity arrows do not cancel, so SO2 is considered a polar molecule. We'll finish this up by assigning our slightly positive and our slightly negative values to our elements in our three-dimensional model, showing again that this molecule is polar. We'll move on to our next example, which is ammonia NH3, which has a trigonal pyramidal molecular geometry. The first thing that we'll do is assign electronegativity values. So the hydrogens are 2.2 and the nitrogen is 3.0. From these electronegativity values, we can determine that our bonds are polar covalent. Then we'll use our polarity arrows to point from the less electronegative to the more electronegative element, so the hydrogen to the nitrogen. And we can see that these bond polarity arrows do not all cancel each other out, so there is a net dipole in this molecule. And we can express that net dipole with this blue arrow over the top of the nitrogen, as everything is pointing towards the nitrogen. We'll move on to our three-dimensional model where the hydrogens will have slightly positive symbols and the nitrogen will have a slightly negative symbol. So like I said before, the electron geometry is tetrahedral when we include that lone pair, and the molecular geometry is trigonal pyramidal. This slight compression of the bond angle can be explained by the non-bonding electron pair on the central nitrogen atom exerting a greater repulsive force on the three bonding electron domains to the three hydrogen atoms. Therefore, when we look at this bond angle over here, we notice that it's not the ideal bond angle of 109.5, but it hovers more around 107. Our next example is chloromethane CH3CL, which has a tetrahedral molecular geometry. Like before, our first step is going to be to look at our molecule and notice what elements are involved. Then move on to assign electronegativity values to all of our elements. So hydrogen is 2.2, 2.2, and 2.2. Carbon is 2.6, and chlorine is 3.2. Then we're going to put in bond polarity arrows from our less electronegative to our more electronegative. So we're going to start with the ones that go from the hydrogen to the carbon. But then we have another bond polarity arrow that is going to go from the carbon to the chlorine. This final bond polarity arrow helps us see that there is an overall net dipole in this particular model. As these hydrogen on the top and the bottom, these arrows cancel each other out. But these two arrows going across do not cancel each other out. So the net dipole is pointing towards the chlorine. This indicates that this molecule, of course, overall will be considered polar. When we go to our three-dimensional representation of this molecule, our hydrogens will have slightly positive values and our chlorine will have a slightly negative value. Let's look at our next example. This is sulfur tetrafluoride, SF4. This has a seesaw molecular geometry. When we look at this molecular geometry, we notice that all the terminal atoms are the same for fluorine, and that there is one lone pair on our central sulfur atom, which will have a definite influence on the overall polarity of the molecule. We move on to assigning electronegativity values to all of our elements involved. So the fluorines will all get electronegativity values of 4. The sulfur will get an electronegativity value of 2.6. So when we put in bond polarity arrows to show that these bonds are polar covalent, the bond polarity arrows will go from the less electronegative to the more electronegative, and again, less to more. Now, these first two arrows that I put in, we're going to say that these first two arrows represent the fluorines on this axial plane, so maybe here and here. Now, the next two fluorines that I assigned bond polarity arrows, we're going to say that these two exist on our equatorial plane, and our equatorial plane also involves this lone pair. And we can see how this lone pair, this fluorine and this fluorine, as I'm going to label right now, are basically spread as far away from each other as possible. But this lone pair is going to make this a polar molecule. So the overall net polarity here would be going from the sulfur to this fluorine and to the sulfur and this fluorine, and then the net polarity would be pointing down somewhere in between these two. So while these two fluorines, those polarity arrows may be canceling each other out, these two fluorines right here, the polarity arrows do not cancel each other out. Therefore, we have a net dipole and the molecule is considered polar. The final thing that we'll do here is assign our slightly positive and slightly negative values to help visualize the polarity of this molecule. Our next example is chlorine trifluoride, ClF3, which is T-shaped. When we look at this molecule, we can see the central atom of chlorine with the same three terminal atoms of fluorine and the lone pair here and here on our central atom. So the next thing we're going to do is assign our electronegativity values. So fluorine is 4, 4, and 4, and chlorine is 3.2. Then we'll see that our bonds are polar covalent and assign polarity arrows going from the less electronegative to the more electronegative. And we can see that these two arrows cancel each other out, but there is nothing canceling out this arrow right here. Therefore, because this arrow is not canceled out, there is a net dipole moment, and the molecule is considered polar. So when we see this, we can see that the chlorine would have a slightly positive charge and the fluorines will have slightly negative charges. Our next example is bromine pentafluoride, BrF5, which is square pyramidal. We can see the bromine as our central atom with the lone pair located right here, and the same 5 terminal atoms of fluorine. So we're going to assign our electronegativity values. So fluorine, 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 and fluorine, and bromine has an electronegativity of 3. So based on these electronegativity values, we can determine that each of these bonds is polar covalent and put in polarity arrows going from less electronegative to more electronegative. And these 2 bond polarity arrows cancel each other out, but nothing is canceling out this final bond polarity arrow. As opposite of that is the lone pair. So a net dipole can be determined in this molecule, which makes it a polar molecule overall. We can see this in this 3-dimensional representation of bromine pentafluoride, where we assign our slightly positive value to our bromine and our slightly negative values to the fluorines. And we'll see an overall net dipole moment. In this case, these 2 images are flipped from each other, where the lone pair is on top here and that other fluorine, which is on the axial plane, is below it, showing the overall net dipole. So what did you learn in this tutorial? We talked about polar molecules composed of polar covalent bonds. And then we looked at examples, and more examples. Need more help? Feel free to contact me. Have a great day.